Okay, so let's come back to our lecture. Okay, so now last lecture we have been starting to talk about the second order homogeneous constant coefficient linear equations. Okay, so that kind of equation is going to take a particular form. Okay, so it's going to take a particular form, ay double prime plus by prime plus cy is equal to 0. This is the general equation. If the equation is equipped with initial values, then it will be an initial value problem. So in general, how do you find the solution of such questions? So you have to write down the so-called characteristic equation, right? So that means you just replace the second derivative by r squared, you replace the first derivative by r, and you replace the zero derivative by a constant. So that's called characteristic equation. Now from the characteristic equation, you're going to solve the two roots, which are going to call it the characteristic roots, right? So now with the characteristic roots, you're going to build this, what we call it fundamental solutions, right? So these are what we call it fundamental solutions. So let me, right? So these are so-called fundamental solutions. Okay, so fundamental solution. And this is the same thing, okay? So these are the so-called fundamental solutions. Right, so you're going to have those fundamental solutions. Now with the fundamental solutions, so the key point here is that if you have a real distinct root, right? So if you're in the case of a real distinct root, that means the discriminant is positive, b squared minus 4ac is positive. Then your root is yt is c1 e to the power of r1t plus c2 e to the power of r2t. Okay, so that's kind of the two fundamental solutions are just raising the characteristic roots into an exponential, and that's it. Okay, what about the real repeated root case? Well, repeated root means that b squared minus 4ac is equal to 0. So the discriminant is just exactly equal to 0, so that the two roots, r1 and r2, are two real roots, but they are the same. Okay, so they are equal to r. In that case, the solution is like c1 e to the power of rt, and then c2 e to the power of rt, but must multiply by t. So that's what we call the golden principle, right? So the golden principle. Okay, so let me maybe I will use another color. Okay, so maybe I use the golden color. Okay, so that's what we call it the golden principle. Okay, so that means you just add a t, insert a t to your equation. Okay, so you insert a t to your previous solution. Okay, so that's kind of the way how you construct solutions to second order homogeneous equations. Okay, how you construct solutions to second order homogeneous equation, and that's what we've been talking about in the previous lecture. Okay, so on Friday. Okay, so now what happened here is that if we go over this whole procedure, okay, so if we go over the whole procedure, so the way you solve, okay, so the way we solve, okay, so basically we can say the way we solve a differential equation is now the same thing as we guess a solution, right? So you're just guessing a solution. For example, last time, if you still remember, we guessed the solution of the type of an exponential function, and we justified that if the exponential function is going to be a solution, then this exponential function must look like, right? So it must look like the characteristic roots, right? So it must admit the characteristic roots in exponents, right? So that's a guess solution. Now, in order to make the guess theory, in order to get the guess theory to be mathematical, you just need uniqueness, right? So it's you actually need two things, right? So one is more obvious that you're going to need existence. So there has to exist a solution, but then you're going to also need uniqueness. And uniqueness is key, right? So this is the key, because if you have two solutions, then what you have guessed does not really make sense, because you might guess one solution, but the real solution is the other one, right? So if there is a unique solution, then you are done, because if you guess the solution, it's like you're looking for a candidate, let's say a candidate to participate in a certain game, right? So if you know that the candidate is unique, then if you find the candidate, it is the candidate. But if the candidate is not unique, then you cannot guarantee that what you found is really the solution. So that's the uniqueness. Is going to guarantee that what you have guessed does make sense, right? So that's kind of the thing. So we want to have like more like a theory, right? So that means that we want to more like call upon a so-called solution theory, right? So you really need such a solution theory. Okay, so you really need such a solution theory that can guarantee you about uniqueness, right? So that's why you need a solution theory. Now, what kind of solution theory you're going to have? Okay, so consider this initial value problem. Okay, so here this equation is in what we call it the standard form, right? So that's the solution theory. You must turn the equation in standard form. So this will be very important. Okay, so that's kind of the thing. So you will need the equation to be in standard form in order to apply any solution theory. Okay, so once it is a standard form, it must look like y double prime of t, right? So y double prime plus pty, right? So plus pt of y prime of t plus qt of y of t, right? So y of t is equal to g of t, right? So it is equal to g of t. With the initial conditions, y0 is y0. So this is going to be a standard form. So remember, the standard form has the coefficient 1 in front of the second derivative. Okay, so standard form of this equation has the coefficient 1 in front of the second derivative. Okay, so as long as you have that, in order to guarantee that you have a unique solution, it suffices to say that the pt and qt and g are going to be continuous on an open interval containing the point t equal to t0. Then there exists a unique solution. Okay, so this the whole theory is actually in parallel to what we have been talked about for first order equation. Remember, the first order equation must take the form y prime plus pt of y is yt, right? So is equal to q of t, right? So q of t. So maybe it's better to use the term g of t, right? So equal to g of t. So in that case, you need a pt and gt to be continuous. We've been talking about such a theory about uniqueness, right? So about uniqueness for linear first order equations some time ago in our lectures. And here is for uniqueness for linear second order equations, situation is completely the same. It's just the equation become more complicated in that you have pt, qt, and gt, the 3 coefficients. And you just need the 3 coefficients to match. Okay, so to match what you would like to have for continuity, right? So if the 3 coefficients matches that continuity, then you're still okay. Okay, so that's kind of the thing about uniqueness theory. Okay, so that's kind of thing about uniqueness theory, right? So that's the uniqueness. Now, the second thing I like to talk about is to construct a structure. Okay, so is to construct a certain structure for these equations, right? So that's what we call it the principle of superposition. Okay, so superposition. Now, why do we need the theory of superposition? Well, it's kind of comes from our observation for the case when you have real distinct root and real, repeated root. In that case, you can see that you always build up 2 solutions. And why is that the case? Okay, so why you want to kind of combine 2 solutions with constant coefficients in front of them? All right, so this is kind of very general. Suppose you're going to have, let's say, linear equations of this form, right? So very general, okay. So, but homogeneous. So this actually is important thing is that it only applies to homogeneous equations. It only applies to homogeneous. Suppose it's homogeneous, then you're going to have this equation. Suppose you have one root, y1 double prime plus let's say p of t of y1 prime plus Q of T of Y1 is equal to 0. Okay, so this must be, okay, so the situation is that this must be a homogeneous equation. Suppose you have this equation. Then you're going to have another one, Y2 double prime plus PT of Y2 prime plus QT of Y2 is equal to 0. Okay, so you have two homogeneous equation, the two solutions of the same homogeneous equation. Okay, so imagine you have two solutions of the same homogeneous equation. Then it is easy to see that because the equation is homogeneous, and therefore we can say that, for example, A of Y1 prime. Okay, so let me say let me use the term C1. Okay, so you can easily see the C1 of Y1 plus C2 of Y2, right? So if I combine these two solutions, take a double prime, and I consider P of T multiplied by C1 Y1 plus C2 Y2, and then take a derivative, and then I'm going to take P of T multiplied by C1 Y1 plus C2 Y2. This is going to be 0. And why is that the case? Because it's easy to see that C1 Y1 plus C2 Y2, if you take a derivative of this object, this is C1 Y1 prime plus C2 Y2 prime, and C1 Y1 plus C2 Y2, if you take a double derivative of this object, is C1 Y1 double prime plus C2 Y2 double prime. So that's kind of the thing, is that it's very easy to see that they're going to have that first and second derivatives going to pass through the brackets and into the derivative of each of them, right? So that's kind of what happens to this homogeneous linear equations, is that if Y1 is a solution, so superposition theory is going to tell you that if you have two solutions, of this differential equation, which is a linear second order and homogeneous, then their linear combination is also a solution. No matter what constant C1 and C2 you take, the linear combination is also going to be a solution. So that's kind of the very interesting phenomenon that's called superposition principle. Okay, so superposition principle. So that superposition principle gives us like a ground, right? So that's theoretical ground of the reason why the fundamental solutions are only the building blocks, in the sense that once you create one solution, E power R1 of t, you create another solution, E power R2 of t, it suffices to consider a linear combination of these two solutions, right? So it suffices to consider a linear combination of these two solutions. So that's what we have for the fundamental solutions, okay, for the fundamental solutions. As long as you have that, okay, so as long as you have that, you can see that the general solution, right? So the general solution of this homogeneous equations, right? So let me consider, okay, so general solution of y double prime plus pt of y prime. So this is very general theory. I'm going to consider such a homogeneous second order linear equations, but not necessarily constant coefficients, just homogeneous and linear, right? So homogeneous and linear in the sense that general solution is going to be y1 of t and y2 of t. These are what we call it the fundamental solutions. Okay, so fundamental solutions, right? So we call it the fundamental solution. As long as you build the fundamental solutions, you can say that your solution yt is c1 y1 of t plus c2 y2 of t. So this is just a linear combination of these two fundamental solutions. Okay, so it is just a linear combination of these two fundamental solutions. As long as you have these two fundamental solutions, the key point is that you want to find a specific solution. Right, so the key point is that you're going to then look for specific solution. Now, with a specific solution, it means that I'll give you initial conditions. So let's say y0 is y0, y prime 0, let's say is equal to y0 prime. With the initial conditions, can we find a solution, right? So can we find a solution? Well, I claim we can do it. Okay, so we can do it by saying that y of 0 is equal to c1 y1 of 0 plus c2 y2 of 0. This is going to be y0, and y prime of 0 is equal to c1 y1 prime of 0 plus c2 y2 prime of 0. This is equal to y0 prime. So this equation, okay, so this equation is just telling you that I can treat, because I can always take y1 and y2, I can calculate y1 prime and y2 prime. As long as I have those fundamental solutions, it is easy to obtain their values at 0. So that's y1 of 0, y1 prime of 0, and y2 of 0, y2 prime of 0. These are quantities that are very easy to be obtained, right? So these are quantities that are very easy to be obtained, right? So as long as you obtain such quantities, you can treat this equation as a linear system of equations that gives you C1 and C2. So from here, you want to calculate C1, C2. As long as you calculated C1, C2, you get a particular solution out of the general solution, right? So you don't really need the general solution, but you immediately obtain the particular solution. Okay, so that's kind of the way how you find C1, C2 for your particular solution. And this is actually what happens in our examples for last lectures, right? So for previous lectures, that's what happens to our examples, right? So for example, we'll be showing you some calculations on Friday, right? So we'll be showing you some calculations on Friday. For example, like this equation, there is an initial condition. Now what I was saying is just an abstraction of this whole procedure, right? So what actually happens is that you put those initial conditions into there, and then from it you can solve for C1, C2. As long as you get the C1 and C2, you get the solution. And how do you solve for C1, C2? You solve for C1, C2 by putting the initial conditions there, and then you make it. Right, so that's kind of the thing. So this is kind of like a theory for passing from a general solution to particular solution. So that's kind of a very general theory that can help you to pass from a general solution to a particular solution. Now, I would like to double check with this theory. Okay, so this theory actually says that y1 of 0 multiplied by c1 plus y2 of 0 multiplied by c2 is equal to y0. So that's first equation. I'm going to write y1, y2 as my coefficients. And similarly, I'm going to have y1 prime of 0 of c1 plus y2 prime of 0 of c2 is equal to y0 prime. So that's kind of going to give you like a linear system of equations. Right? So if you have such a linear system of equations, then we're going to ask when does solution C1 and C2, right? So C1, C2 unique. Right, so when is the solution C1, C2 unique, right? So that's kind of a problem, because even for linear system of equations, you might have no solution, or you might have infinitely many solutions. But we want just one particular solution. Like the problem has to be well posed, right? Has to be well posed. When is the problem well posed? Well, if you have a linear system of equations, then it means that if you want linear system of equations to have a unique solution, then it just suffices to say that the determinant of the coefficient matrix has to be non-zero, right? So that's like, this is the question, right? So that's the determinant of the coefficient matrix has to be non-zero, right? So this determinant. Now, if you look at this determinant, okay, so let's look at this determinant, right? So look at this determinant, or sometimes we say it is the determinant of the coefficient matrix y1 of 0, y2 of 0, right? So y1 of 0 and y2 of 0, right? So y2 of 0. So this is the so-called coefficient matrix, y1 prime of 0 and y2 prime of 0. This is what we call the coefficient matrix, right? So if you look at the determinant of this coefficient matrix, it takes a very particular form, right? So what form does it take? Well, the first line are going to be the functions, right? So the first line are going to be the functions, and the second line are going to be their derivatives. So that's kind of very clear, has a very clear structure, right? So that's kind of very clear structure. Like the first line are going to be the values of the functions, y1, y2, and the second line is going to be their derivatives. So these y1, y2 are the so-called fundamental solutions, right? So these are the fundamental solutions that you really found in your guessing, right? So that's a guessing theory, and you have to first guess your fundamental solution. but when is it really fundamental, right? So if it does not give you a concrete C1, C2, you cannot really say it's a fundamental. So when is it really fundamental? It is really fundamental in the sense that this matrix has to have a determinant that's non-zero. So this is a very important quantity. Okay, so we're going to call it W of Y1 and Y2. It's going to be determined as Y1 and Y2, the functions are on the first line, and their derivatives are on the second line. So that's what happens here. And it is also going to be written as determinants of Y1, Y2, Y1 prime, and Y2 prime. Okay, so it's also going to be written as a determinant of Y1, Y2, and Y1 prime, Y2 prime. Okay, so that's kind of the very important matrix that we're going to call it the Wronskian. Okay, so we're going to call this matrix the Wronskian. The Wronskian really comes from probably Polish mathematician Wronskian. Okay, so Wronskian did a lot of studies in the ordinary differential equations. That's why this object is named after him. Okay, so the Wronskian. So what we have here can be said like the Wronskian. So it's the same thing as saying the Wronskian of W1 of Y1, Y2 at point 0 is not equal to 0. So in general, the Wronskian is actually, so here is implicit, but indeed, we can say that the Wronskian is actually a function of t, because each of these functions, as well as their derivatives, are functions of t. So the Wronskian is indeed essentially a function of t, right? So essentially, the Wronskian is a function of t. As long as the Wronskian is a function of t, the Wronskian is non-zero, right? So the Wronskian is non-zero. Okay, so W, Y1, Y2 is non-zero. It's going to suffice this to check that Y of t is equal to C1, Y1 of t plus C2, Y2 of t has a unique C1, C2. In that case, we're going to say Y1, Y2 are fundamental solutions, right? So, so there's kind of it's kind of a really double check that you're really going to have fundamental solutions. Because if you don't have this unique C1, C2, you cannot build a general solution from Y1, Y2. In order to build a general solution from Y1, Y2, you have to guarantee that a particular solution C1, C2 is unique. And in order that is going to be true, we're going to have the Wronskian is going to be non-zero. Okay, so that's kind of the three equivalent statements. Saying that Wronskian is non-zero is the same thing as saying that Y of t is C1, Y1 plus C2, Y2. That means a unique particular solution, and the same thing as saying that Y1, Y2 are the fundamental solutions of the system. Okay, so that's kind of the Wronskian theory. And the Wronskian, okay, so I can tell you that the Wronskian is going to be a very important object throughout these lectures. Okay, so it is going to be a very, very important object throughout these lectures, and we're going to encounter it many, many times. Okay, so we're going to encounter it many, many times. So therefore, it is kind of completely necessary to understand the structure of the Wronskian. So what's the structure of the Wronskian? Remember, it is a determinant. First of all, it is a determinant. Okay, so how does determinant go? Well, determinant is being calculated, right? So if you want to have a determinant of 2 by 2 matrices, so that basically it says that determinant of Y1 and Y2 is going to be a determinant Y1, Y2, Y1 prime, and Y2 prime. And how is you have that determinant? Well, determinant means that you cross product these two minus you cross product these two. So that's Y1, Y2 prime minus Y2, Y1 prime. So this is essentially how you calculate the Wronskian. Okay, so in general, it is a determinant, but you have to obey the rules of how determinants are being calculated. Okay, so it is Y1 multiplied by Y2 prime minus the Y2 multiplied by Y1 prime. That's what you have for the determinant. Okay, so that's the determinant. So the Wronskian is actually a determinant, which can be actually written as Y1, Y2 prime minus Y2, Y1 prime. Okay, so you just want this determinant to be non-zero in order to build a set of fundamental solutions, fundamental solutions. Okay, so that's kind of the thing about this Wronskian business. Okay, so now let us come back to what we've been talking about at the beginning of this lecture. Now, does the Wronskian of these two is going to be non-zero, right? So you say you want to have fundamental solution, but is it really a fundamental solution? Well, you have to check the Wronskian, but it is easy to check. So it's easy to check that the Wronskian, right? So the Wronskian of e to the power of r1t is e to the power of r2t. What's going to be the Wronskian? The Wronskian is going to be a determinant. The first line are going to be the functions, e to the power r1t, e to the power r2t. The second line are derivatives, so r1, right? So e to the power of r1t and r2, e to the power of r2t. As long as you have this, you calculate, it's going to be r2 minus r1 multiplied by e to the power of r1 plus r2 of t. So, and this has to be equal to non-zero because the two roots are not the same. So that's really the case, right? So in that case, the Wronskian is non-zero, and therefore the two solutions are corrected to be are safe to be fundamental solution. You combine them. That's our theory, which we taught you on Friday, right? So, and what about this one? Well, you have to calculate e to the power of rt and t times e to the power of rt. I leave it to you as an exercise. Okay, so I leave it to you as an exercise how to calculate the Wronskian in this case. Okay, how to calculate the Wronskian in this case. So that's kind of the thing about this Wronskian, and it is very, very important. It is a very, very important object that I would like everybody to make sure that you understand it. Okay, so that's you have to make sure that you understand it. So here is the definition of the Wronskian. The Wronskian of two functions. Okay, so it's very, very general, not necessarily fundamental solution, but no matter what kind of function you give me, I can always calculate the Wronskian as a determinant, where the first row are the functions, the second row are the derivatives. So y1, y2, y1 prime, y2 prime, you calculate determinant, that's y1, y2 prime minus y2, y1 prime, that's going to be the Wronskian. So that's how you calculate. Okay, so that's how you calculate the Wronskian. Okay, so that's how you calculate the Wronskian of such a problem. Okay, so that's how you calculate the Wronskian of such a problem. Okay, so that's about the Wronskian business. Okay, so that's about the Wronskian business. Okay, so that's about the Wronskian business. Okay, so that's kind of the thing about this Wronskians. Okay, so that's kind of thing about this Wronskian. Now let me formulate the whole thing that I've been talking about into a theory. Okay, so let me formulate the whole thing that I've been talking about into a whole theory. Okay, so the theory says that suppose y1, y2 are two solutions of this differential equation, y double prime plus pt of y prime plus qt of y is equal to 0, and the initial conditions y of t0 is y0, y prime t0 is y0 prime, then it is always possible to choose the constants c1, c2, such that the linear combinations yt is equal to c1, y1 plus c2, y2 is also going to give a solution with initial conditions if and only if the Wronskian is not 0 at the initial point. Right, so this is exactly what we have been talking about in our previous 30 minutes, is that in order to guarantee such a linear equation with constant coefficients to have unique solution, in particular for y1, y2, or in the sense that y1, y2 are fundamental solutions, and c1, c2 can be found uniquely, that means you have to take the Wronskian, where the Wronskian is just a determinant, y1, y2 prime minus y2, y1 prime. If you evaluate the Wronskian at the initial point, previously the initial point was 0, but it doesn't necessary to be 0. It can be a general t0, right? So if that is the case, then you just need the Wronskian to be non-zero. Okay, so that's kind of the theory that we've been talking about in the past 50 minutes. So this gives us, okay, so this gives us kind of a theoretical ground, like you have, like this is the ground. Okay, so this is the ground for guessing, right? So it gives us a theoretical ground for any kind of possible guessing that you're making throughout these lectures, right? Throughout this course. But if you guess, it's okay to guess, but you have to guess two solutions, right? So you have to be correct, not just once. You have to be fortunate. You have to have fortune for twice, right? So that's we have to be lucky twice. And once you are lucky twice, you find two solutions. and you find two solutions, you say that these both are fundamental solutions, in the sense that the Wronskian is not going to be 0. So you should evaluate the Wronskian at point, initial point, no matter what it is. Usually its initial point is 0, but maybe the initial point is 1 or maybe any other point. But it's completely fine. You just want to check that this is the Wronskian. It should not be equal to 0, right? So that's what you have for the Wronskian. Okay, so the Wronskian says that the Wronskian has to be non-zero. And if that is the case, then the general solution is only a linear combination of the two fundamental solutions. And if the fundamental solutions are there, you can put initial condition, everything will be safe because the Wronskian is non-zero. So in that case, there's another terminology, or we can say, okay, so y1 and y2 are linearly independent. Okay, so sometimes we also say that they are linearly independent. Okay, so this is just terminology, and we will come back to this terminology later in this course. But here, let me just say, linearly independency is the same thing as saying fundamental solutions, and the same thing as saying the Wronskian is non-zero, and same thing as saying that particular solution exists and is unique. Okay, so that's kind of the linearly independence theory. Okay, linearly independence theory. Okay, so here I would like to show you an example. Okay, so I would like to show you a very nice example. So here it says that you take two functions, f, t, and gt. If their Wronskian is t, and ft is 1/2, gt is 1, can you find gt? So what does this mean? Well, it means that, first of all, what's the Wronskian of two functions? Well, according to what we have learned in the past 30 minutes, if you take two functions, then their Wronskian is saying that the first row are the functions, the second row are the derivatives. So that's going to be fg prime minus f prime g, right? So that's going to be the Wronskian. And you know the Wronskian is t, so that's the Wronskian must be equal to t, but you know f is 1/2. So if where f is 1/2, you can put 1/2 here into this equation. That's going to be 1/2 g prime, this is t. So the gt is t squared plus constant. So that's kind of an easy differential equation that everybody knows how to solve, right? So as long as you solve it, you just put t equal to 0, if g0 is 1. So t equal to 0, it tells you that constant is 1. Therefore, you're going to have the solution. gt is equal to t squared plus 1. Right? So that's going to be the gt is equal to t squared plus 1. So that's going to be your the way how you have the solution. Okay, so how you have the solution. Okay, so that's kind of you can see that this is one of our exam problems, right? So it was one of our exam problems just to examine if you know what is a Wronskian, right? So it doesn't examine anything, but just to ask you, do you know what's the definition of the Wronskian? As long as you know the definition of the Wronskian, you can solve this problem without any problems, right? So that's kind of the thing about this Wronskian business, right? That's kind of the thing about this Wronskian business. Okay, so that's kind of the summary, right? So it's going to say that the general solution of of this homogeneous constant coefficient, homogeneous linear equation, is going to have a family of solutions. Y of t is c1y1 plus c2y2, and this family of solutions is going to include every solution if and only if where the Wronskian is not 0, right? So if and only the Wronskian is non-zero. And if you have the non-zero Wronskian, we're going to say that you build a fundamental set of fundamental solutions, and linear combinations is going to give you a general solution. Okay, so that's kind of the interesting phenomenon. Okay, so interesting phenomenon and very, very important because now we're doing a theory, right? So we're not just doing like empirical guess of your solution theory, but we are actually doing quite a theory about finding the solutions. Okay, so here let me make a small remark here that the fundamental solutions can be found by stating that the fundamental solutions themselves are linear combinations of themselves, and therefore you can set the initial conditions to be different values with different initial conditions at derivatives, you're going to be able to find a fundamental solution. Okay, so here I won't talk much about this, which is not very important, but they're on the lecture notes that you might take a look. Okay, so you might take a look. Okay, so that's kind of the thing about this whole theory. let me make a final remark here. Okay, so let me make a final remark here. Okay, so what happened here is that, so it looks like, right? So it looks like when we check the Wronskian, it comes from this whole argument where you want to find the C1, C2, right? So if you remember, in order to find this constant C1, C2, you need the coefficient matrix to have a non-zero determinant. So that's one the way how it helps you to check the Wronskian comes out. But it looks like in order to make this theory to work, the Wronskian must be evaluated at initial points. It's just that you need the Wronskian at the initial point to be non-zero. Okay, so what actually happened here is that it looks like up to here, where we're actually ignoring that initial point. We're just saying that the Wronskian is non-zero, but we're not referring to at which point the Wronskian has to be non-zero. So is there any kind of problem here? Well, there's no problem here by the following theorem. Okay, so here's a nice theorem due to Aber. Okay, so Aber was one of the world's best mathematicians in history. Okay, so one of the world's most prominent mathematician in history. But unfortunately, so he's a Norwegian mathematician. Okay, so who has beautiful works in equations, right? So in complex analysis and many other fields. Okay, so very, very important mathematician. Unfortunately, he didn't enjoy much of his life. Okay, so he kind of passed away because of too hard work, and that damaged his health. Okay, so he died at the age of 27. Okay, so at a very young age. I think it's probably just a few years younger than all of you, and older. Okay, so and just a few years younger than me. Okay, so he died at a very early age, but made essential contributions to mathematics by many theorems. So here's one of his theorems. It's just about this differential equation. It says that the Wronskian is actually an exponential function. So what does it mean, an exponential function? Exponential means that if the Wronskian, so it's a constant multiplied by an exponential, and the exponential is never zero. So that means if the Wronskian is non-zero at one point, it must be non-zero everywhere. You agree with me? So what does it mean? It means that if the Wronskian is non-zero at one point, then the constant must be non-zero. And if the constant is non-zero, the Wronskian is non-zero everywhere. So that's kind of a nice theory. It kind of tells you, gives you a theoretical background why we ignore that t. Because we just need the Wronskian to be non-zero at a certain point, no matter which point it is. You can say I want to check an initial point, but not necessarily so. Okay, so you can even check that I check the Wronskian at any other point is non-zero, then it is completely fine. You don't really need the Wronskian to be non-zero at a certain point, but the Wronskian can be non-zero like no matter where it is. If it is non-zero at one point, it is non-zero everywhere. So that's a very, very nice observation. Okay, so that's a very, very nice observation. It kind of tells us that you only need to check the Wronskian at one point instead of everywhere. Okay, so that's kind of a nice point. So that means that the Wronskian is either equal to zero on a whole interval, or it is never zero on a whole interval. Therefore, if you want to check that the Wronskian is non-zero, you just have to check at one point, right? So you just have to check at one point. So that's kind of a very nice question. Okay, so that's kind of a very nice question. Okay, so that's kind of here. I would like to show you one last example. Okay, so I would like to show you one last example. That's just to summarize today's lecture. Okay, so it's a for semester 2012 and final exam. Okay, so this is an example that was talking also about the theory for ordinary differential equations. Okay, so look at this example. So it says that, can you determine the longest interval in which such an initial value problem is guaranteed to have a unique twice differentiable solution, and do not find a solution? So what's this equation talking about? Well, this equation is basically something, right? So it's basically something like standard form, right? So it's kind of, is this equation in a standard form, like this question? So let's come to the question. Is this equation a standard form? Can anybody answer my question? Is this equation in a standard form? Anyone has idea? What does it mean standard form? Standard form means the coefficient in front of the second derivative must be equal to 1. Is this the case? Anyone has idea? I want to hear from you.
No, it's not.
No, it's not the case, right? So this is not in a standard form, right? So you must be very clear. This is not in a standard form. So that means, you see, in order to have a unique solution, we said that in order to have a unique solution, if the equation is in standard form, you just need the coefficients to be continuous. That's enough, right? So if the equation is standard form, you just need the coefficients to be continuous. That's enough. But if it is not in a standard form, like what you see here, then you have to first turn into a standard form by dividing t's on both sides of this equation. You divide by t, right? So you divide by t on both sides of this equation. As long as you divide by t, it suffices to say that these coefficients must be continuous. How to make this coefficient continuous? It suffices to say that t cannot be equal to 0, t cannot be equal to 2. So you just avoid 0 and 2. You avoid these 2 points, 0 and 2. And therefore, the longest interval must contain the point 1, because you start an initial condition from 1. Your initial condition starts from point 1. And it has to avoid 0 and 2. So that interval is actually 0 and 2 with open interval. So that's the open interval on which you're going to have a continuous a unique solution. So you can see that even this part of the knowledge, not just the Wronskian, right? We've been talking about the Wronskians all the time. But at the very beginning, we've been talking about the solution theory. When do you have a unique solution? And unique solution is guaranteed if the standard form of this equation has continuous coefficients. It is very important to guarantee that it is the standard form of this equation has continuous coefficient. And therefore, it looks like this question is like you have to turn your equation in standard form before you proceed with anything. Right? So these kind of questions, I can say they're really tested on the exams. Okay, so but it doesn't mean they are not tested. Okay, so from time to time they're going to test it, and you can see that this one was 14 points on one of those final exams. Okay, so that's kind of the thing about the theory. Okay, so let me briefly summarize. Okay, so that's kind of the thing about the theory for second order equations. Okay, so for second order equation. Now, once this theory is built, we should come back to our story about second order homogeneous constant coefficient linear equations, right? So we should come back to this theory about these equations. Namely, in order to find a solution, now we understand that if A is not equal to 0, you can always turn the equation in standard form. So that's not a problem at all. And therefore, we have been passing through the characteristic equation theory. As long as you have the characteristic equation, the two roots of the characteristic equation might give you a set of fundamental solutions. But unfortunately, if they are going to be a collapse, they are going to be equal, then you cannot build two functions that are the same. Why? Because the two functions are the same is going to result in a 0 Wronskian. You can check by yourself. If you don't have the t, then the Wronskian is going to be just 0, which means that it's not going to be a general solution because you cannot find the two constants. Now, when do you have the Wronskian good enough? Well, you have to multiply by t. In the case of double root case, you multiply by t, you should be able to create a well-behaved Wronskian. So that's kind of the theory, right? So that's kind of the theory. And what has been left is the complex roots. By complex roots, it means the discriminant b squared minus 4ac is now negative, right? So if you have complex root case, then you don't really know. Okay, so you don't really know how to find a solutions, right? So how to find a solutions. So therefore, we have to kind of spend some time on the complex root case. Okay, so we will spend like 5 minutes for today's lecture for the complex root case, and we will continue. Okay, so we will continue in the next lecture. Okay, so that's kind of the to complete this whole theory. Okay, so to complete this whole theory, we have to also talk about the complex root case. What does it mean, complex roots? Well, if you have this equation ay double prime plus by prime plus c of y is equal to 0, you have such an equation, then you're going to find the characteristic equation ar squared plus br plus c is equal to 0. That's the characteristic equation. As long as you have the characteristic equation, you're going to check the R1, R2 from the discriminant, right? So that's kind of what happens here, is that b squared minus 4ac is positive. Then you're going to have two distinct roots. R1, R2 are real. R1 is not equal to R2. This is being solved, right? So already solved in our previous lectures. Now what happens here is that b squared minus 4ac is equal to 0. You have R1, you have R2. They're going to be real, but R1 is equal to R2 is equal to R. This is already resolved, both resolved. Now this is what you have been left is the case that b squared minus 4ac is negative. In that case, you're going to see that R1 and R2 are going to be equal to minus b plus minus the square root of b squared minus 4ac, right? So divided by 2 times a, that's kind of a quadratic formula. But this one, in this case, b squared minus 4ac is negative. So how do you take a root of a negative number? Well, in order to take a root of a negative number, you can use high school complex variables. So that's kind of going to be plus minus the square root, actually 4ac minus b squared divided by 2a multiplied by I. Right? So in our complex, in your complex numbers, right? So what you have learned in high school about complex numbers tells you that I is such a quantity that I squared is equal to minus 1. Right? So if you square this I, it's going to be minus 1. So as long as you have this, you can see that these two roots are actually take the form lambda plus minus I times mu, where lambda is equal to this one. Right? So let's say this is lambda. And the mu is equal to this quantity, lambda plus minus I times mu. Is a good parabolic, right? So these are so-called complex conjugate roots, right? So these are the so-called complex conjugate roots, right? So these two roots are in the complex conjugate. By complex conjugate, it means that they're going to share the same real part, but their complex part, their imaginary part, are going to be reciprocal to each other. So that's kind of a pair of complex conjugate roots. Now, as long as you have the complex conjugate roots, how are you going to find solutions? Are you going to just say that e power lambda plus I times mu and e power lambda minus I times mu? Well, that's going to be sophisticated because you really don't know how do you going to raise a complex number to exponential. So that's not going to be really the case, right? So that's not going to be really the case because you really don't know how do you raise an exponential to a complex power. So you won't have such a story, right? So the story won't look like this, right? So how do you find a set of fundamental solutions in the case of complex conjugate roots, right? So complex conjugate roots. So that's kind of the problem. Okay, so now what happens here is that there is going to be a solution. Okay, so there is going to be a solution that we would like everybody to memorize. Okay, so there's going to be a solution. We're going to ask everybody to memorize this solution. We're going to say that the real part enters the exponential and the complex part enters sine, cosine. Okay, so let me just end up with the solution. Okay, so the general solution is going to take the form y of t. Okay, so it's c1 e to the power of lambda t and plus c2 e to the power of lambda t. Real part enters the exponential means that lambda is going to be the real part, which is going to enter the exponential. And complex part, I would say, enter sine and cosine. So that means the solution must take the form like the cosine and sine. So that's kind of the thing. So cosinuses of mu t multiplied here by sinuses of mu t. So you can see that the common real part is going to enter the exponential. And the common complex part is going to enter respectively a sine and cosine. So this is going to be your y1 of t, and this one is going to be your y2 of t. And that's the general solution is still a linear combination of the y1 and y2. So that comes to the question, right? For example, we've been talking about the Wronskian. What is the Wronskian of these two functions here? E to the power lambda t of cosinuses of mu t and e to the power lambda t of sinuses of mu t. What's going to be the Wronskian, right? So I will leave to you as an exercise. Can you calculate such a Wronskian maybe after these lectures? Okay, so maybe after these lectures. Okay. So that's what I want to say. Okay, so for today's lecture, okay, so we will come back to our next lecture. When we resume the lecture, we will continue with the complex conjugate root case. Okay, so let me finish here for today's lecture, and I'll see you in the next lecture. Okay, so and that's all for today. Okay, and see you later.